Thank you, Christoph, for this kind introduction. Well, this presentation, I would like to focus on the inner circularity of a steel plant, which is actually today a quite dusty road still. So still, this is not the most prominent topic in a steel plant. It's a lot of residuals, dust, sludges, and also slags, which need to be somehow handled and treated. But nevertheless, this will be also a key topic for circularity and also for green steel to handle also these solid byproducts and residuals. But at first, let's have a look on some numbers. If we have a look on today's integrated steelwork, so integrated steelwork route, we see that there is a lot of residuals generated, so dust, sludge, and slag. But we also see that especially the slag coming from the blast furnace is a very valuable byproduct and can be utilized in a very good way also in other industries. As we all know, steel industry is undergoing a huge transformation nowadays. And one might think, since we are producing green steel in the future, also the topic of residuals and slags and byproducts could get better or even be solved. But if we have a look on the figures and looking what the transformation in the first step to a, let's say, high-grade DR-based route via electric arc furnace or a scrap-based electric arc furnace route means, it shows us that we get in total less amount of residuals, but also, let's say, different residuals and new byproducts which need to be treated and need some solutions to, let's say, make this in a profitable way into a valuable byproduct. If we go via the smelter route, and this is also one of the topics why using a smelter is an interesting fact for some customers, we create a very similar byproduct as we have it nowadays from the blast furnace. So the slag from the smelter as a pre-smelting aggregate is a valuable byproduct and can be used. So all in all, we can sum up that the total amount of residuals is getting less, but the number of critical residuals which need to be special treatment is even getting more. And therefore, we have to take care about this. But still, let's remain in today. What is done with the residuals? Sometimes it's landfilling. Even if the integrated steelworks route is highly optimized, still some of the byproducts need to be landfilled. And typically, this is a global indicative figure, about 20% of the dusts nowadays are landfilled. And from the blast furnace slag, it's only 2%, which is currently landfilled globally, which shows again the high value of this byproduct. But for the BOF and EAF slag, already nowadays, 30% of the slags are landfilled because there is no economic way at the moment to treat them and to reuse them. And this is not only a fact of, let's say, environmental impact, it's also an economic fact. If we consider the total steel production and assuming now an average iron content of 35%, we're talking about 20 million of tons per year of iron which are getting lost every year and not reutilized. And considering also landfilling costs of approximately 50 euro per ton, which differ a lot. For example, in Korea and Japan, landfilling is almost impossible due to the scarcity of land they anyhow have, whereas in other countries, landfilling is more or less for free. We're talking about 2.7 billion of dollars or euros, which are paid every year for landfilling. So this is a huge waste of material and creates also a huge environmental impact. And what we are seeing coming up is that there are more stringent environmental regulations, especially regarding these solid byproducts, are coming up, and new legislation is also to be expected in some countries all over the world. Also, the European Union has identified the circular economy as a focus topic, and it's already part of the European Green Deal Circular Economy Action Plan. And also, as we see here on the right side, as shown also from World Steel, we see here the 4 R's which are defined for, let's say, the circular economy, where I would like to give you a short overview on the reuse part, so let's say the internal circular economy of an integrated or future steel plant. And this is also why we are here today with this conference, to talk about all these aspects of circularity which are crucial for a modern and successful steel plant in the future. So let's have a look on today on the byproduct streams of an integrated steelwork. We should not forget that the integrated steelwork as we know it today is a highly optimized process and plant which has decades of optimization, and each integrated steel plant has its own recycling unit, the sinter plant. So many of the dusts and residuals which are created are put on the sinter strand, which agglomerates them, and they can be used inside the primary process again. So typically this figure is about 10% of the overall sinter feed are residuals, which is a huge amount which is consumed by the sinter plant. Nowadays, most of the dusts which are created are briquetted and put back to the blast furnace or to the basic oxygen furnace to reuse them. But still, some of the dusts need to be landfilled because we have also the other environmental aspect that during steelmaking process, a lot of emissions and pollutants are created, and these pollutants need to be removed from off-gases. But when we remove them from the off-gases, they're not gone and disappeared. We just use some additives or some other material which we put into the off-gas stream to bind these components, to extract them from the off-gas, not to go to the air. But still now we have the problem then in the solid residuals, because we shifted up to a certain part the pollutants from the gaseous to the solid phase. Sludges are in a similar way like, let's say, dust, partially briquetted, but a lot of them need to be still landfilled. The by far biggest amount in terms of mass is of course slag, where especially the blast furnace slag is a huge amount. And the blast furnace slag has a very good product quality which can be used in cement industry and has a very positive impact on carbon dioxide emissions of cement industry, and is therefore a very interesting byproduct and a very good example for cross-sectional cooperation and cross-sectional benefits also. So also in the past, steel industry, and we tried to support our customers in that regard, we made a lot of developments for the existing integrated steel plant to improve the circular economy or the waste or residual material streams. For example, for the dust, we developed processes to extract the, let's say, harmful substances from the dust to recover the iron and the valuable fraction and to minimize the pollutants or the harmful fraction to absolute minimum. I will show you this process later on a little bit more in detail to give you a feeling of an example of such a recovery process. Also in terms of slag, we did a lot of developments like dry slag granulation to utilize also the waste heat which is inside the slag, mainly for blast furnace slag, and also processes like zero waste process to, let's say, separate the iron fraction and the mineral fraction from the slag and also remove, let's say, harmful substances to recover these valuable byproducts. Why are not hundreds of these plants currently in operation? The simple reason is economics. If we talk, for example, about the zero waste process, we're talking about the small steel plant inside the steel plant. It's a kind of electric arc furnace which needs to be operated and which has certain OPEX. So meaning this is also always a question, what is in terms of landfilling, and also, of course, in terms of legislation, what can be done or what should be done. But if we have now a look into the future, with the new steelmaking routes coming up, the transition and transformation of the steel plants, we will have direct reduction plants and electric arc furnace in the steel plant, perhaps in some or few steel plants at the beginning, a smelter. And we will have typically a complete different waste material stream because we're losing the sinter strand, the sinter band, which has a very positive effect. So what possibilities do we have? We of course can briquette, so agglomerate the dusts again and feed it to the electric arc furnace which needs more electricity than there, or feed it to the direct reduction plant, also knowingly that this will have, from pure process point of view, let's say, limited positive effects. For dust from electric arc furnace, which is mainly based on scrap and has a high content in zinc, there is the possibility to extract the zinc from the dust, which has a certain value and can be sold as a byproduct. I will also show you this process a little bit more in detail later on. The biggest challenge for sure will be the slags. For the smelter, we have the advantage that the slag is similar to the blast furnace and an external usage will be possible. Especially for the electric arc furnace, the slag, I would still call it an unsolved question. There are technical possibilities, but there is not only, let's say, one solution, because it will depend on the amount of slag, as well as on the, let's say, certification and the possibilities to use the slag at the end of the day. And as we have heard and seen before, I think the topic of scrap sorting and crafted scrap will get even more important, because the best thing in all these recovery steps is to avoid all these pollutants going into the process to extract them at the end of the process. So now I would like to show you a short video, just as an example, how such a recovery process could look like. This is now for dust recovery and treatment. We call it the so-called byproduct leaching process. It can be applied for technologies like Meros, so it's for desulfurization. In principle, it can be applied for any dry dedusting solution which adds certain amounts to the off-gas stream to remove the harmful substances. So here you can see the dedusting unit on the right side, and here on the left side you see the leaching plant where we extract and recover the material. This plant is built in Japan, where this plant is now in operation since 3 years. So why is the leaching process called? The simple answer is we take the dust, the solid and dry dust, and dissolve it in a tank to dissolve the solvable components like sulfur and all these elements, to extract them to the water phase. All the insoluble solids are typically the value ones, so iron and carbon, and these we can then recover by filtration and drying. So we separate again the valuable fraction of iron and carbon and feed it back to the primary process. In this case it was a sinter plant, but also in other metallurgical aggregates it can be used. This is, from an environmental point of view, the most important step, the removal of the harmful substances. Because the bad substances like dioxins and any other poisons we removed before from the off-gas, we have them now in the water, and we have to remove them with precipitation and certain chemical treatment to extract them again out of the water phase. Why do we do this? We have then the benefit that we really can concentrate these substances in a very small mass, and this is only the really remaining pollutant part, which then needs to be specially treated, like in waste incineration plants or landfilling, which needs a final treatment. And what is remaining is more or less a polished water, water which can be discharged if you are close to the sea or to your water treatment plant. And we have a final filtration step with sand and activated carbon to be sure that none of the pollutants slipped through the whole treatment. Why should we do this whole process? The benefits are clear. We are reducing the total amount of residuals which need to be treated or landfilled or deposited, whatever, by 90%. And in this case, we could recover 30% as a valuable material and 30% treat in such a way that they can just be discharged. Only 10% of overall pollutants remain, and of course, these need a further treatment. So this was just one example showing the principle more or less of any residual treatment step. The question is always how to reduce the mass of the bad substances and concentrate it in a smaller fraction. Last but not least, the final example, also what we can do about the dust. It's the so-called zinc extraction process. So nowadays the dust from many mini mills or scrap-based steelmaking routes is fed to so-called Wälz process, where crude zinc oxide is produced and the so-called Wälz slag. This process is in terms of, let's say, recovery rate, also in terms of environmental impact, has some topics, let's say. Therefore, we developed together with Montana University Leoben a so-called two-step zinc recovery process, where we, let's say, split the wets process into a calcination step and a melting and reduction step. Why do we do this? We have the big advantage that we can, let's say, remove in this first step all the bad substances from the dust, yeah, and can treat them specifically, and then, let's say, feed this remaining material to a melting and reduction agent where we can create the high zinc oxide fraction, a metallic fraction, which can be used as a scrap substitute, and a mineral fraction, which can be then used in cement industry. So the challenge is, of course, there needs to be a certain amount of zinc, otherwise the economic rate for recovery is not given. Yeah? And there's huge potential because even if many or some of the plants will be fed with DRI, also still there is a lot of plants fed with scrap, which will lead to a high amount of zinc in the dust. So, to come to my conclusions, I think it's very important also to address this internal circularity of a steel plant, because at the end of the day, it will make the difference also in terms of competitiveness of each steel plant and also in the definition and labeling of green steel for each steel plant. So this is a part of the overall green steel topic, and as we see, all these works have been done in the past. For the integrated steelwork, they highly optimized their waste material streams, and the same exercise must be done for the new transformed steel plants. Yes, so also in terms of conversion costs, it will be very important to, let's say, have a proper byproduct utilization and management. And of course, we as Primetals are open and would like to support you with all your different pathways. And I would also like to emphasize that we are also a development partner in that regard, because especially when it comes to the byproduct topic, it's not a straightforward topic like a core metallurgical aggregate. There are many specific boundary conditions for each plant, and also the input material is very different in every region, in every plant. So this needs some specific tailoring, and we are, let's say, based on our experience, the right development partner for approaching these topics for a sustainable future. So that's it from my side. Thank you very much for your attention and looking forward to some questions.
Thanks a lot, Thomas, for sharing with us so many technologies and ways how to optimally recycle byproducts in a steel plant. We've received some questions. Maybe just pick out one of them and just answer them. Mm-hmm.
Well, I will start with the last one. I think I answered it partially also in the presentation. The byproduct leaching I showed to you, this plant is running in Japan at JFE exactly. Yeah. Why is it in Japan and not in Europe? The answer is simple. Especially in Japan, the situation with landfilling and the scarcity of land is very high. So therefore, let's say the topic is even more pressuring steel plant operators than it is in Europe, actually. And perhaps the question above, what future solutions will be required to achieve optimal circularity? Well, I think that's actually the issue with this internal circularity. There is not one solution that fits all. Each steel plant has very specific boundary conditions. Yes, some have their own deposits, some have a special material what they have to use and what they produce. Even if we have a look on the dust composition from, for example, BOF dust, how much this differs from every plant to each plant, yeah? And this brings actually the difficulty that there is not one solution which we can now roll out to every plant. It needs an individual approach and an individual analysis for each plant to bring, let's say, the most economic solution for each specific requirement.
Okay, super. Yeah, thanks a lot, because we already ran out of time. Thanks again, Thomas.